Hi, my name is Audun Bottrud. I'm a principal research scientist at MIT and Argonne National Lab, and I have the pleasure of chairing this panel, which is on research topics that are close to my heart. It's on renewable electricity generation and smart grids. Those are topics I work on myself as well, and it's also obviously very important for the climate challenge that we are addressing in this conference, given the potential for a very important role in the decarbonization of the energy system through cleaning up the grid and decarbonizing additional, or electrifying, I should say, additional sectors of the economy. So I'm happy to say that we have three very prominent speakers in the field here in this session, and we are going to cover a quite wide range of topics from solutions at the end user to more systems and market solutions. So just before we get started, a couple of logistical reminders. Please ask your questions in the Q&A box that you can see in the Zoom window, and you can also enter more general discussions in the chat box for the audience. So with that, let me introduce the first speaker. The first speaker is Professor Bert Hesselink from Stanford University. He's a professor in electrical engineering and also with an appointment in applied physics. He did his PhD from Caltech in 1977 and has a long and distinguished career in academia and industry. He is a worldwide leader in development of ultra-high performance optical data storage systems, and is also a pioneer in internet-assisted learning. So I think we can learn from you also for how to organize conferences like this. He has founded two companies, Cirrus Technologies and Zenvid, and he has a long list of awards and recognitions. I'll just mention a couple of them. That includes he's a member of the Royal Dutch Academy of Arts and Sciences, and he was a member of the Hubble Space Telescope Committee. According to his bio, his current research interests span the areas of ultra-high density optical data storage and nanophotonics, but I would dare to add that he's also interested in solutions to the energy and climate problem. And I'm very intrigued by the title of his talk, which is Dispatchable Solar and Wind Power Without Batteries. So with that, over to you, Bart.
Okay, thank you, Audun. Can you hear me properly?
Yes.
Okay, let me share my screen here, and okay, can you all see this?
Yep.
Good. Well, thank you very much for the invitation to speak here, and the topic is a little bit outside maybe optics that I've been working on for a significant fraction of my career. But it's actually somewhat related because of the fact that we're dealing here with nonlinear acoustic power, which of course satisfies the wave equation, but the implementations are very different. And one of the topics that we're interested in, this is actually work that is being done at a small company that Tim Gibbons and I started, Nirvana Energy Systems, which is located in Ohio, in Cleveland, close to the Glenn Research Center from NASA, where the original technology on Stirling engines was developed. But maybe a couple of sentences in background as to how I got involved in this was that about 6 years or so ago, Tim Gibbons, who is a former dean of the School of Engineering at Stanford, and I were at a party for the department, and so I asked him what he was doing, and he said he was working on solar panels. And I said, well, if you want to do PV, then maybe the better way to go would be to kind of do solar thermal, because you can make that black body radiation extremely efficient. And so he said, well, why don't we just do something? And I said, okay, started looking into it. And of course, what you need to do in that case is build a heat engine which essentially operates between two different temperatures. And to make a long story short, it turns out that the most efficient way to do that is to use a Stirling cycle. And this has been worked out, but it turns out that the essentially concentrating solar is not so attractive from a number of perspectives. And so we built something else that I'm going to talk about today, which is a thermal acoustic engine. And it has some very unusual properties compared with what normally a Stirling engine would do. So without further ado, let me go into some of the details here. So one of the problems, as most of you all know, is that solar and wind are notoriously unreliable power sources. And you might say, well, why is that really a problem? Well, it is a problem because if significant amounts of solar power go into the grid, for example, then you have issues with both voltage and frequency regulations, and it is not predictable. And so when the percentage of integration of solar and wind becomes too large, then there is a real issue about how to actually develop a grid that can take this distributed power, which is unreliable, and compare it against reliable sources, base sources, such as nuclear power or gas-powered engines that are producing the electricity. On the other hand, standalone systems have different problems, namely that if you do buy a solar wind system with batteries, which I have done. I have a place up in the mountains which is totally off the grid, and every 7 or 8 years you have to fork out maybe $25,000 in batteries because the solar system is totally off grid. And so in the wintertime, even if you have very significant capacity, like 80 or 90 kilowatt hours, you still can get only a few days of support. And so when it's snowing in the mountains, that is not working either. So you need to have a standby either diesel or gas generator. And the last part, which is a problem, is that if you have on-grid distributed residential solar systems, when they actually are designed for grid, they don't work very well off-grid. And so you need to kind of have another system that deals with that. So the solution that we are proposing for this is to essentially provide a thermoacoustic power stick, which we refer to as TAPS, that uses natural gas or any type of fuel to provide a full hot water and space heating system. And it turns out you can use the same cycle to do cooling as well. And you can achieve more than 90% efficiency in a 2 to 3 year payback. You may say, well, yeah, but that's not totally green. I totally agree with that. And so there's certainly other options here because it is an external engine. It could also be utilized in a hydrogen environment, for example. But it turns out that there is actually a way to sequestrate the CO2 and make it actually CO2 neutral, even although you're burning natural gas. And so the units that we're looking at for homes are about 2 to 4 kilowatts, electrical power 15 to 35 kilowatt hours, or kilowatt heat. And these can be connected in a distributed power plant. It's actually a completely remotely accessible system and under the IoT approaches. It turns out that in California, there's a very strong need for this kind of a product. We've been talking to PG&E because, as you all know, wildfires require now that PG&E turns off power to millions of users. And even solar alone would not be suitable. Then you have to buy significant amounts of batteries. And why does this not go further? So one way to show that this is the case is you might think in the Caribbean, for example. If you look at Trinidad and Tobago, these are 2 islands that actually have a lot of natural gas, but you would think also there would be a lot of sunshine there in the Caribbean. Well, if you look at the statistics, it's roughly about 200 days or so. So the solar power solution alone is not good enough. And so if you look at the average daily demand curve what you find is that you can do a calculation of the levelized cost of energy, which essentially is just a ratio of the amount of money that you have to put into the system divided by the number of kilowatt hours that you get out of the system. And so there is a way to calculate that, including all the maintenance and upfront costs, etc. And so as an example, if you took a 10 kilowatt off-grid generating facility, then you still need to provide significant amounts of power outside the solar installation time periods. And you also see that over time, the demand curves are varying. And so to do a careful analysis, one of the things that is always important is it's not just to say that you have 3 kilowatts of power, because when the way that is now specified, that's typically only at noontime. But it is also that this power is not always available. There's lots of fluctuations in it. And if you now include batteries, most of the time, you cannot really deplete them either. So the amount of battery that you need to store energy into can be 25, 30, or 40% higher than what you might think on the basis of just the capacity. So if you then compare the taps versus the diesel generator, and do that with, say, solar and some batteries, there's a program called Homer that is being utilized in the industry to kind of calculate what then the lowest cost of energy is. And what you find is that for diesel generators or any other gas generators, it's the cost of maintenance and replacement over a 20-year period that increases the LCOE cost significantly. So on the basis of this kind of accepted calculation, you can calculate the LCOE, and what you find is that if you use taps with solar and wind, for example, then that would be the lowest cost, or use taps with gas standalone. And you might say, well, why is that cheaper than solar and wind? That is because when you actually look at the additional investment that is needed, then that brings up the cost over the lifetime of the system. So the message is that, yeah, we can't do it with solar and wind alone, so we need to do something else. And so we started out, as I said, 6 or 7 years ago. It was an idea. Neither one of us really knew what we wanted to do or what we were doing, but you know, kind of in typical Caltech fashion, if you don't know the subject, just read a book and become an expert. So we tried that, and we created some funding from Floodgate as a seed investor, and then friends and family. And friends are very, very rich billionaires, so that helps a little bit to get some funding into the company. So what we want to do is creating some game-changing technology and products which are different than what have been developed so far. And at the same time, we also want to reduce the global warming gases. And this essentially is done through a system that has the size of a hot water heater, as you can see on the right-hand side, below the Nirvana Energy System side. And then the generator, and there can be some additional storage as well for hot water, which is the byproduct of creating electricity. So the thermoacoustic power stick would be a micro combined heat and power system. 4 kilowatt electrical efficiency greater than 30%, and system efficiency 90% or higher. We have quite a few fundamental patents. Turns out this technology and the way we do it has never been built before. And from an economic perspective, the break-even should be less than 5 years, and the target is 2.5 years. If you look at current Stirling engines, the break-even point may be 15 or more years. And the same is true actually with solar panels, etc. as well. Solar systems also have a long break-even point. We can think that we can increase this probably up to 40 kilowatts. And the cost target should be roughly about less than $6,000 for a core kilowatt system. So Why is this significant? Well, here's an example where combined heat and power has been strongly promoted. This in the UK. And the basic problem is that even though the boiler for hot water may be very efficient, if you look at the power coming out of the power station, it's roughly about 32%. In the US, it's roughly about 33%. So there are very significant losses over the total system. And if you actually produce both power and heat at the same time, the same amount needed from the separate systems, then your losses go way down by an order of magnitude, and your efficiency goes way up. And that translates in a reduction of greenhouse gases. It turns out that the amount of global warming gas by heating this gas and by power is roughly about the same over the year. And so you can reduce that by 50–60%. And so if you look at the annual market for hot water heaters, for example, is about 12 million or so. If you had a reasonable, say, less than 10% or so fraction of the market, the world market of these hot water heaters, if you actually turn them in MCHP systems, then you would have a significant ability to reduce global warming gases, and up to about 5%. So the profit for the consumer is somewhere in the order of about $1,000 to $1,700 per year. So you can see that, you know, it's anywhere between 5 and 3 years or so if you have that price point that you can actually break even, and thereafter over the remaining 15 or 17 years you'd make between $1,000 and $1,700 a year. So you would say, well, why isn't there a market for that? The unfortunate part is that all the Stirling engines on the market and any other technology is way more expensive, and it's not available. And actually, President Obama sent out an order in 2015 that the government should promote MCHP. So to a certain extent that has happened, but recently there is a different type of administration. How does this work? Well, here what we have is a pipe that you can see. It's this person, his name is Mark, is holding in his hands. It is just a glass tube, and there's a metal screen in there. Just think about this as one of your sponges in your kitchen. And what he's going to do is he's going to heat it up, and you'll hear what happens. Here we go. So the metal screen here is in the center. What it does is it essentially produces a temperature increase in the gas, which then results in a change in the density and the volume, and that sets up a pressure wave, which then resonates inside the tube. So heat is converted into pressure waves. A standard approach to a Stirling engine cycle is a alpha Stirling cycle, and in this case, what we do is essentially have a different arrangement where there is a piston. The piston produces an acoustic wave, as you know. It's a sine wave and compression and expansion. The pressure wave then induces a particle movement. And so as the gas goes through compression and expansion, the particles move back and forth. So even although what you see is there is a propagating wave, if you look at the red dots, you see that the helium particles locally only oscillate back and forth. And so the big benefit of this is that now you can actually go through an acoustic cycle called the Stirling cycle, by which the system essentially produces an amplification of an incoming wave. And the way that is done, and I'll come back to this in a moment, but think about this in the following way. The piston moves to the right, it creates a compression wave, and then it goes into a section there where there is a cold heat exchanger and a hot heat exchanger. And those heat exchangers are stationary. And assume that this one is at 300 degree Kelvin, say maybe, and the other one is, let's say, at 800 or 900 degree Kelvin. Then what happens is you have a linear temperature gradient in which there is the 300 Kelvin temperature at the cooler side and say 800 or 900 at the hot side. And so if the gas is moving to the right, so the red dots are moving to the right, then they are in the compression phase being exposed to heat that is being delivered to the gas, and thereby increases the pressure. In the other half of the cycle, the gas now is moving, the red dots are moving from the hot side to the cold side. Now they go through a cooling cycle, and so energy is taken out of it. And as a result, what you get, the Kenton amplification ratio that is proportional to the ratio of the absolute temperatures. In between is the regenerator. The regenerator is essentially a heat storage device. During the time that you actually put heat into it, it gets heated up, and the time that it goes back in the expansion wave, it gets cooled. And so it's essentially just a storage. It would work without the regenerator. The problem is the efficiency would be significantly smaller. Now, on the right-hand side, you then have a second amplification stage, and then the resultant acoustic wave, which is essentially multiplied by the ratio of these amplification ratios, say 4 to 6, then goes into a piston which generates electricity. The important part about this cycle is that if you look on the lower right-hand side, we have the Stirling cycle, which is the standard one, which was invented over 200 years ago in Scotland. And the problem is that it's very complicated mechanically, and that's primarily due to the fact that there are hot pistons that have to operate both in cold and hot temperatures, and you need to maintain very tight tolerances, and so mechanically these have been very complicated. I don't want to go through all the details, but what is important, and the message that I like to keep with you is that the gas velocity and pressure need to be in phase. Hold on 1 second here, because I may have to go a small operation. Hold on. Hello? Yeah, speaking. Yeah. Okay, thank you very much. Bye-bye. I'm very sorry, but I have to undergo a hopefully small surgery. And this was the doctor that just called me. And I need to head over to the hospital here at Stanford. Originally, I was told that this was going to happen at 2 o'clock, and that's why we scheduled this earlier. But I'm very sorry, but I won't be able to complete this presentation.
Thank you for getting us this far, Robert, and all the best of luck with the